Hello, I am 3STEM. Uh, Mr. Lou here, and I'm going to be teaching you today about Lesson 8.5. And the title of the lesson is Trigonometric Form of Complex Numbers. This is actually pretty exciting stuff, and so I'm really happy to be able to do this for you. I wanted to remind you, you know how when we've been working with trigonometry, we've been able to break angles into component parts by getting an x value from the cosine and a y value from the sine, and being able to represent triangles or parts of triangles by using the angle and the magnitude of the radius and things like that, along with the cosine and the sine to represent the x and the y coordinates, respectively. So that's what this lesson is about. There's some great things that kind of come along with this that, when you get to talking to somebody about using polar notation or being able to represent vectors using the complex numbers and complex number system. This works out really nicely. So hope you enjoy this. Let's go ahead and go into it. Okay, so here we are. This is lesson 8.5. And this is only part one. There's going to be more to this after today. These are trigonometric forms of a complex number. So what will we learn in this lesson? Let's talk about this. And this is, I'm going to read that right-hand side first. Why are we learning this? So you remember we've been able to break triangles into x and y components using cosine and sine of the angle multiplied by the radius. If we consider complex numbers in the same way, there are practical uses for this form, and that we can take advantage of these things. So this is good stuff. So what will we learn? First thing is that we're going to learn how to plot complex numbers in the complex plane. We're going to learn how to write trigonometric forms of complex numbers, how to multiply and divide complex numbers written in trigonometric form. And then we're going to learn how to say this guy's name and know how to use his theorem. The how to say it is de Mauve. And I know it doesn't sound that way, the way that it's written, because you might want to try to say de Moivre, but that's not what it is. It's de Mauve's theorem, and to find powers of complex numbers. So, and then finally, how to find nth roots of complex numbers. That'll come in the second part. All right. So we get into talking about, first of all, this thing called the complex plane. So just as you were able to represent real numbers on a real number line, and complex numbers can be represented on a complex plane. So this is also known as the Argand plane and is represented by z is equal to a plus bi. As the point a comma b is in a coordinate plane that represents and that represents the complex plane, the horizontal axis is called the real axis, and the vertical axis is referred to as the imaginary axis. So here are two complex numbers plotted in the complex plane as you look at this picture right here. So you see on the horizontal, that's labeled as the real axis. The vertical axis is labeled as the imaginary axis. And so you see 2 points here. 3 comma 1 can also be written as 3 plus I. And think about that. The coefficient of I there is 1. So notice that that point it has a height of 1, but it moved to the right 3 in order to show that point right there. Likewise, the point -2, -1, or -2 minus I is a point that goes on this plane to the left 2 and then down 1. And so it's being represented on the real axis and the imaginary axis of this thing called the Argand plane. So as we talk about this, one of the things that we're going to be interested in here is called it is also referred to as the magnitude, but it's also called the absolute value of a complex number. The absolute value of a complex number, a plus bi, is defined as the distance between the origin 0, 0 and the point AB. So if z is equal to a plus bi, the absolute value of this complex number is represented as, look at the notation. You've got the absolute value bars surrounding a plus bi, and then that's equal to the square root of a squared plus b squared. So it looks very Pythagorean, or very much like the distance formula, because it is representing the distance from the origin to that point. So if the complex number a plus bi is a real number, that is, if b is equal to 0, then this definition agrees with that given for the absolute value of a real number. So as we're looking at that, then you just have zeros there representing the I portion of it, and that's equal to the absolute value of a. And remember, absolute values are always positive. All right, so let's get into this now. We're taking a look at the example 1, finding the absolute value of a complex number. So we're given the number z is equal to -2 plus 5i, and we need to find its absolute value. So let's do that here. And so we're just going to say then that the absolute value of z is equal to the square root of -2 squared plus 5 squared. And that's going to be the square root of 4 plus 25, or the square root of 29. And so that square root of 29 is the absolute value of this complex number z. Okay, moving right along. We're talking now then about this thing we call the trigonometric form of a complex number. So long in the past, you have learned how to add, subtract, multiply, and divide complex numbers. We will now focus on working with powers and roots of complex numbers. And to do this, it is helpful that we write complex numbers in trigonometric form. So looking at the figure on the right there, consider the non-zero complex number a plus bi. By letting theta be the angle from the positive real axis, measured counterclockwise, to the line segment connecting to the origin and the point AB, you can write that a is equal to r times cosine of theta, and that b is equal to r times the sine of theta. So remember, a is going to be on the x-axis, b is how far from the x-axis or parallel to the y-axis, but in this case it's the imaginary axis. So as we look at it this way then, we also know that the measure of r is the magnitude. It's that distance from the point to the origin. So r is then going to be equal to the square root of a squared plus b squared. And then we say that a plus bi is equal to r cosine theta plus r sine theta times I. This is the trigonometric form of a complex number, because you've got the trigonometry in there. You've got cosine and sine, right? And so that's the trigonometric form of the complex number. So this is going to become more important, and you'll see why we're going to be using this as we develop this. So just to get this into it a little bit further, the definition then, the trigonometric form of a complex number is z is equal to a plus bi, can be written as the magnitude r, or the absolute value of a plus bi is r, and that times cosine theta plus I sine theta, where A is equal to R cosine theta and B is equal to R sine theta. And R is then equal to the square root of A squared plus B squared. And also, by the way, the tangent is always going to be described as equal to tangent of theta, then is going to be equal to the value of B divided by A. So if we wanted to know the value of the angle, you could take the inverse tangent then of the ratio B over A. The number R is referred to as the modulus of Z, and theta is called the argument of Z. So just those are the names, and you have to just kind of remember those things as part of the definitions of things. The trigonometric form then of a complex number is also called the polar form, because there's infinitely many choices for theta. The trigonometric form of a complex number is not unique. Normally, theta is restricted to the interval of 0 to 2 pi, and although on occasion it is convenient to use even theta equal to something less than 0. Okay, so in this example, example 2, we're going to be writing a complex number in trigonometric form. So when we're given z is equal to -2 minus 2 root 3i, we want to write that in trigonometric form. So that's going to start off with knowing the modulus, or the distance from the origin. So we're going to just say then that r is going to be equal to the square root of -2 squared plus -2 root 3 squared, and we'll get the square root of 4 plus 4 times 3 is 12, and that turns into the square root of 16. So our modulus r is going to be 4, because the square root of 16 is 4. And so now we're going to be looking at this in complex form. And so one thing you might want to do is even just go ahead and plot it. So I'm just going to do that really quickly. We're going to go to the left 2, and then we're going to go down 2 root 3, so that's a little further down. And so we're going to be looking kind of like that. And we know that that's got a length of 4, and we're going to use the tangent of theta. Tangent of theta, if you remember, is going to be b, which is -2 root 3, over a, which is -2. So we have negative over negative, that's positive, but we know that we're in the third quadrant, so we just have to kind of keep that in mind. Tangent is positive in the third quadrant. And so as we take that, we're really looking at, since -2 cancels -2, we're talking about tangent of theta equaling root 3 over 1. So we're really looking at something like this then, aren't we? In the third quadrant, we're talking about the value of b as negative root 3 and 1. So we know that we're in the third quadrant, and we know that that's a 30, 60, 90 because of the relationship of the root 3 and the 1 for the lengths of sides, and that equates to about a relative angle of 60 degrees, which is pi thirds. So in the third quadrant, pi thirds, that makes theta then equal to 4 pi thirds. So 4 pi thirds, and now we can write our number in trigonometric form. So we need the modulus, and so we have z then is going to equal the modulus, which is 4, times the cosine of our theta. So it's going to be 4 pi thirds plus I times sine of 4 pi thirds. And there we have it. So I'm going to take this down to where the book then has a copy of that picture that I just drew. There it is right there. And then I'll just paste the complex number written in trigonometric form. So example 3 says writing a complex number in standard form. So here we are, we've got a complex number, or a number written in trigonometric form, and we need to write this in standard form. So let's go ahead and do that. Let's take a look at, we have a cosine of negative pi thirds. So if you remember, that's going to look kind of like this. We're talking about negative pi thirds. Looks like this. Pi thirds is, of course, it's a 30, 60, 90. That makes this 60 degrees right here-ish. And that means that we are, if that's 60, then this is going to be negative root 3 over 2. That makes this 1/2. And that makes this 1, right? And so we can pretty much say we know what the cosine of negative pi thirds is. That's going to be 1/2. So we'll just go ahead and call that 1/2. And plus I times the sine of negative pi thirds, and that's negative root 3 over 2. So we've got that, and that's times the square root of 8. Out in front. So if we go ahead and multiply that through, now remember 8 is 2 root 2, so we're going to call that 2 root 2 over 2 plus, and we're going to call this, not plus, because that's going to be minus because it's negative, minus, we'll say 2 root 2, but times 3, so, but that cancels the 2, and so we're just going to call that root 6, I. So our answer ends up being then square root of 2 minus root 6 I. And that's my new z written in standard form. All right, this next topic in this next section is where this really gets exciting. We're talking about now the multiplication and division of complex numbers. Now, that may sound really scary, but now that we understand how to turn complex numbers into their trigonometric form, multiplication and division of complex numbers becomes a total breeze. And so here is the benefit of why this subject is taught. The trigonometric form adapts very nicely to multiplication and division of complex numbers. And I'm just going to kind of lead you into this, and hopefully you'll follow along and appreciate through some of your trig identities why some of this stuff works. So suppose that we're given two complex numbers, and one of them is z1, where z1 is going to be equal to the modulus r1, and have the angle theta, the argument, be theta 1. So we got the cosine of theta 1, and we have I times the sine of theta 1. And then z2 has a modulus of r2, and the argument, or the angle theta, of theta 2. So there's two different angles. One is theta 1 and one is theta 2. And so z2 then is made up of r2 times the cosine of theta 2, and then that r2 times I sine theta 2. Now, if we wanted to find what the product of z1 and z2 is, we just really multiply both those parts together. So when we do that, consider what we're seeing here. You see we have z1 times z2, so we have r1 times r2, that's totally fine. And we have cosine of theta 1 plus I sine theta 1, and cosine theta 2 plus I sine theta 2. Now, if we just take those two binomials on the outside there, on the right-hand side, and multiply them like they are, two polynomials, we get the benefit of having like terms come together and all that stuff. So you'll see then where cosine of theta 1, cosine theta 2 comes from. That's firsts. And then you have the outers is going to be cosine theta 1 times I sine theta 2. And the inners is going to be cosine theta 2 times I sine theta 1. Well, all that kind of creates a bunch of different like terms that we can factor out pieces like I and or even evaluate I as I squared is I is -1. So that's where this negative comes from. That's from I being -1. But anyway, the whole thing comes out to be this, that z1 times z2 then becomes r1 r2 times the cosine of theta 1 times the cosine of theta 2 minus sine of theta 1 sine of theta 2. And maybe you recognize that, maybe you don't, but it's cosine of theta 1 minus theta 2 plus theta 2 because there's the minus in between, so it's a plus. So it's cosine theta 1 cosine theta cosine of the sum of theta 1 plus theta 2. That's where this part right here comes from. And then there's the plus and there's the I, so we factor out the I. And look at this other part, sine, cosine, cosine, sine. Well, that's the sine of a sum, sine of theta 1 plus theta 2. So when we pull this all together, look at this. We have the product then of z1 times z2 is equal to r1 times r2 times the sum, the cosine of a sum, theta 1 theta plus theta 2, and I times the sine of a sum, theta 1 plus theta 2. Dude, that's the cosine of a sum and the sine of a sum. So there we are, multiplication and division of complex numbers. All right, so let's go ahead and see how division then just naturally follows. So we have the first one. That one works this way. And if we're dividing instead now, this just happens to work out this way, and there is a proof of that, but I'm not gonna flesh that out. But now we're talking about division being z1 over z2, or we're taking two complex numbers and we're doing a divides on it. So that becomes r1 over r2, and that becomes times cosine of the difference, theta 1 minus theta 2. Plus I times the sine of theta 1 minus theta 2. So really all that we have to do now is just learn how to apply these things. So now we're talking about multiplying two complex numbers. So here's two complex numbers in example 4. Find the products of the complex numbers. Here's z1 is 2, the modulus is 2, and the argument is 2 pi thirds, so we're in radians here. So here we see cosine of 2 pi thirds plus I times sine of 2 pi thirds. And that whole thing becomes, that, z1. z2 is a modulus of 8 times a theta of 11 pi 6. So we've got cosine of 11 pi 6 plus I times the sine of 11 pi 6. And so there that is. So we've got z1 then times z2 becomes 2 times 8. There's our moduluses, or moduli. And so we got 2 times 8. And then that times cosine of 2 pi thirds, I'll put this in parentheses, plus 11 pi 6. And then we say plus I times the sine of, same thing, 2 pi thirds plus 11 pi 6. Just about ran out of space there, but there we made it. Okay, let's just go ahead and combine these things. So we have then z1 times z2 is going to equal 2 times 8 is 16. And we have, by the way, 2 thirds is 4/6. So we got 4 pi plus 11 pi over 6. And so that ends up being 4 plus 11 is 15 pi 6. but they're both divisible by 3 on top and bottom, so that becomes 5 pi halves. So with that being 5 pi halves, then our number, that becomes our theta. So theta is equal to 5 pi halves. And so we can write the product, z1 times z2, is equal to 16 times the cosine of 5 pi halves plus I times the sine of 5 pi halves. And then we know what 5 pi halves is, because we can just draw that over here. Here's 1 half, 2 halves, 3 halves, 4 halves, 5 halves, and we know the values there. So cosine of 5 pi halves is 0, and sine of 5 pi halves is 1. So this is just going to be I, and I have 16 plus that. So I end up with 16I is my product of z1 times z2. Example 5, we're dividing now. So as we divide, we have this number right here, z1, and we're going to be dividing that by z2. And z1 looks like that. So we're just going to go ahead and go into this. So z1 over z2 is going to be 24, which is the first modulus, divided by the second modulus, which is 8. And then we're going to say times the cosine of 300 minus 75. And that's plus I times the sine of 300 minus 75. And there's our whole expression there. Now, cosine of 300 minus 75 is the cosine of 225. Let's fix that up a little bit. 225 degrees plus I times the sine of 225 degrees. And that's all divided by 24 divided by 8 is 3, multiplied by that. So z1 divide by z2 is going to equal 3 times the cosine of 225 degrees. Now, 225 degrees is right here at 45 degrees, isn't it? In the third quadrant. So that's negative, and so it becomes negative root 2 over 2. And then it's also negative for sine, so it becomes minus, we'll just call it this way, root 2 over 2I. Now that times 3, and so I end up with z1 divided by z2 is equal to negative 3 root 2 over 2 minus 3 root 2 over 2I. And there is once again our complex quotient of z1 over z2. All right, that's it for this lesson. There's some exciting stuff. You might want to go back over and take a look at what I did to solve some of these things. And here is your homework, and I'm going to make this homework that is due sometime next week. So take a look at that when I assign it in Google Classroom. And if you'd like, I'm happy to meet with you during office hours. So maybe send me an email or something like that saying you want to attend and you want to talk over some of these things that maybe you are missing as far as understanding goes. And hope you guys are all staying safe, and we'll talk to you later.